All right, here are perfect problem 3 solutions for Math 112. This problem deals with Newton's law of cooling, which is stated right here. And kind of all the variables are defined in here. T of t gives you the temperature at time t. Annoying that it's capital T and a lowercase t. I know, it's because temperature starts with T and so does time. T of S is not the starting time. Also kind of annoying about this formula. It's the surrounding temperature. So think about it as like the room temperature. T naught is what your liquid, the thing in question here, starts out as. And again, this little t up here is time. K is a constant, just depending on what the liquid is. Some liquids hold their temperature better than others. So what we're going to do is use this formula to answer a bunch of questions. First thing we're going to try to figure out is what is K? What is the constant for this liquid in question? How well does it hold its heat? Well, we can figure it out by using this formula here and plugging in these numbers. So suppose that you have a liquid that is 100 degrees in a room that is 60 degrees. 2 hours later, you measure the temperature to be 70 degrees. Let's plug in all the pieces. 2 hours later tells us that T equals 2. At time 2, the temperature is 70 degrees. So I have 70 equals T with a little s in the subscript is the surrounding temperature. So the room temperature, room is 60 degrees. I guess that's a 60 right there. Plus T naught is the temperature that the liquid started out as, and it says that it starts at 100 degrees. Minus the surrounding temperature shows up twice in this formula. E to the negative K times T. Well, T is time, and since everything is in hours here, I'll go ahead and make that my units. So 2 hours later, I'll make this negative 2 times K. And what I want to do is solve for K. I could do that and subtract 60 from both sides, and you get 10 equals 100 minus 60 is 40, e to the negative 2k. So divide both sides by 40 and you get that a quarter is equal to e to the negative 2k. So now you're trying to solve for k, maybe you think to take the natural log of both sides of the equation. So you get natural log of a quarter equals negative 2k. And to solve for k, we could divide both sides by negative 2. Instead of dividing both sides by negative 2, I'm going to do something slightly different. I'm going to multiply both sides by negative 1/2. And the reason I'm going to do that is I'm going to try to do this problem without ever using a calculator. And so if I had divided by 2, it would have made it less obvious that I can use my third log rule here. So I can take that negative 1/2 and bring it up into the log and say that k is equal to the natural log of 1/4 raised up to the negative 2 power, negative 1/2 power, sorry. The nice thing about that is the negative in negative 1/2 power means take the reciprocal of it. So this is the natural log of 4 raised up to the positive 1/2 power. But 4 to the 1/2 power is the square root of 4, which is just 2. So what I get is that k is equal to the natural log of 2. And with this more simplified form of k, it'll make it easier for me to do the rest of the problems without a calculator. Again, you don't need to do this. You could have stopped here, I guess, and type this into a calculator, and you probably get you get some decimal that's equivalent, or at least approximately equivalent to the natural log of 2. At any rate, this is 1 over here. I guess I should label my work. And now I'm going to move on to part 2. And part 2 has lots of different scenarios. 2a says that if the liquid was 210 degrees and was placed in a room that was 50 degrees, how long would it take? So now we don't know what t is. We're trying to solve for t. But fortunately, we have k. We've solved that before, so we'll be able to solve for t. How long would it take for the liquid to cool to 90 degrees? So it sounds like 90 degrees is the temperature at time t. And that's equal to, if I kind of copy down my formula here, the surrounding temperature given to me to be 50 degrees plus the initial temperature minus the surrounding temperature. Initial is 210, surrounding is 50. E to the negative k. Well, we figured out k was the natural log of 2 times t. Be careful, this is not the natural log of 2t. It's the natural log of 2 times t. So now we want to solve for this. I think I'm going to deal with some of the numbers first before I worry about using any exponent rules over here. So if I subtract 50 from both sides of the equation, I'd get 40 is equal to, and 210 minus 50 is 160. So I got 40 is 160, e to the negative t. Yeah, do I want to write it like that? Sure. Negative t times the natural log of 2. I'm just going to reverse the order that I write these in so it's a little bit more obvious that I'm only taking the natural log of the 2, not of the t. Gets me here. If you divide both sides by 160, you'd get a quarter is equal to this mess. Sure, I'll show it in another step. And you might recognize, well, there's an e and a natural log there. It'd be cool if those would cancel out. I mean, they almost do, but they don't because of this negative t here. It kind of gets in the way. If this were e to the natural log of something, the e and the natural log could cancel each other out in some sense. But it's not because of the stupid negative t. But you can deal with that. You can use your third log rule, just like we did down here. You can take this coefficient and bring it up into the exponent of the log. So I could say 1/4 is equal to e raised up to the, get rid of that tiny little dot, e raised up to the natural log of, and I'm going to take the log of 2 to the negative t power. And what's nice about that form is e to the log base e of something is just equal to that something. In other words, this whole thing simplifies down to just 2 to the negative t power. This you might be able to solve. You might be able to just look at it and tell that t is equal to 2. If you couldn't, I guess you could take the log base 2 of both sides of the equation. The log base 2 of a quarter is negative 2, because 2 to the negative second power is equal to 1/4. So what I got was that t was equal to 2. If you had used a calculator in this decimal approximation and plug stuff in here, maybe you got t is 1.999999 or 2.0001 or something really close, depending on the accuracy of your calculator. But it turns out the exact answer is 2. It'll take exactly 2 hours to do this. Okay, 2b. If the liquid takes 4 hours, so time equals 4, to cool from 80, my initial temperature, to 35, what I end up at, so I got 35 equals, what is the surrounding temperature? So what's not given this time is T sub S. That's okay. Leave that as an unknown and we'll solve for it. So I got 35 equals T sub S plus the difference between the initial temperature given to me to be 80 degrees and T sub S times E raised up to the negative K times T, negative K. Well, K is still the natural log of 2 and T in this problem is given to me to be 4. So I got negative 4 times the natural log of 2. I think it'll probably benefit us to simplify this exponent first. And in fact, it'll be pretty easy to simplify because it's going to be the same thing we did over here. Like remember here I had e to the negative t times natural log of 2, and I brought the negative t up into the exponent so I could rewrite the whole thing as just t2 to the negative t. It's kind of hard to say. I could do the same thing here. I could take the negative 4 up into the exponent. So I'm going to leave everything else the same. But now I have e raised up to the natural log of 2 to the negative 4 power. And e to the natural log of something is just equal to that something. So I got 35 equals T sub S plus 80 minus T sub S times 2 to the negative 4th power. Sure, I'll write that. 2 to the negative 4th power is the same as 1 over 2 to the 4th power. 2 to the 4th power is 16. So this is 1/16 right here. So I got 35 equals T sub S, what I'm trying to solve for, plus, if I take this 1/16 and I kind of distribute it into these exponents, I got 80 over 16 minus T sub S over 16. Well, 80 over 16 is just 5. So I got 35 equals maybe 16/16 of T sub S. That's what this is. Plus 5. Minus 1/16 T sub S. And so really all I did was simplify each of these guys. I rewrote this in an equivalent form, this, and this. But the reason I wrote it like this is it might make it easier to combine like terms now. I can subtract 5 from both sides of the equation to get 30 over here. And then 16/16 of this thing minus 1/16 of this thing is equal to 15/16 of this thing. So T sub S is equal to 30 times, multiply both sides of the equation by 16/15. It's hard to say. And the 30 and the 15 cancel to give me 2. 2 times 16 is 32. I find that the surrounding temperature must have been 32 degrees. All right, one more. 2C. Guess that goes down here. I might have to implement a whole bunch of arrows to get this to fit, but what are you going to do? If the liquid is left in a 60-degree room, there's my surrounding temperature. For 3 hours, there's T. At which point its temperature is measured to be 90 degrees. Okay, so that's what it ends up as. So 90 equals the surrounding temperature was 60 plus, what was the initial temperature of the liquid? T naught. I don't know T naught. It's not given to me. That's what I'm asked for. Okay, leave it as T naught. T naught minus 60 times E raised up to the negative K, natural log of 2, times T, but T is 3 in this case. So I'm going to write negative 3, natural log of 2. You might be able to see the shortcuts that we're doing here. Maybe I can skip a couple steps. 60 minus 90 is just 30. So 30 is T naught minus 60 times, well, if I took this negative 3 and brought it up into the exponent, I'd have e to the natural log of 2 to the negative third power, aka 2 to the negative third. 2 to the negative third is 1/8. So if I multiply both sides by 8, I get 240 equals T naught minus 60. And now add 60 to both sides. And hey, check me out. I didn't even need to draw arrows, but I'm afraid that won't print at the bottom, so maybe I will draw one arrow. Add 60 to both sides, and you get T naught was 300 degrees. Your liquid started out at 300 degrees in order to satisfy the rest of those criteria. Pretty hot. Not that that matters. And that's about all that I got. I think that answers all of the questions here, so I'll call this video good.